So today we have a talk from Ciska Kemper. You know her well. She has made her PhD in 2002. I saw that in Amsterdam, and then went around the world, a few years in USA, in England, and then for nearly 10 years, as I thought, 8 years in Taiwan. And she also passed our program scientist Germany.
Garching, yes, for a few years, yeah.
And now she's here for 4 years already, and ICREA professor. And we will today talk about mineralogy of silicates. So please.
Thank you. So yes, it's very nice, of course, to speak to the home audience, and I will today be talking about the mineralogy of silicates in the diffuse interstellar medium. And this is a JWST project that I'm doing with some long-term collaborators. I think it's a very exciting project, so I wanted to share this with you. It's still a work in progress, so I'm giving you sort of the current status. I was hoping that it would be finished by now, but you know, best laid plans, no? So here we are. Now, why would you want to study interstellar dust? Well, dust plays, this brief little introduction is to explain to you that dust plays an important role in galaxy evolution. And it regulates a number of things. First of all, it has an effect on the energy balance in the galaxies, on the interstellar radiation field. And you can see this very well when you look at spectral energy distribution of a galaxy. This blue component here is the light that is emitted by stars directly. And then a lot of that light is absorbed by or scattered by intervening dust in the interstellar medium. That dust then heats up and starts radiating in the infrared. And you get this infrared excess here on top of the spectral energy distribution, which kind of takes away this part of the stellar light. So you're having a reprocessing of the light in galaxies, and typically about 30 to 90% of a galaxy's starlight, is being reprocessed in this way. The exact amount depends on the amount of dust, the level of star formation, etc. And talking about star formation, dust also plays a role in star formation itself in two ways. One way is actually the wrong one here. Does this point as well? No. In one way is through the chemistry. So dust provides a service for chemical reactions to take place. A lot of chemical reactions do not take place in the gas phase, but require this dust service to actually proceed at rates that actually give rise to a reasonable amount of gas of that molecule in the interstellar medium. And some of these molecules are really important in providing the cooling that is necessary for star formation. So if you're collapsing clouds to form stars, you need to get rid of excess energy. This can be done through cooling, through molecular species, but actually dust itself directly can also provide this cooling. So dust plays an important role in star formation as well. So all in all, I think the presence of dust is not only a tracer of star formation, but it's actually a necessary requirement for star formation. And given its role that it plays in star formation and in the energy balance of galaxies, it actually, we can safely say that it drives galaxy evolution. So this is to indicate the importance of studying interstellar dust. And then the next thought that you may have is like, okay, well, what is interstellar dust made of? And we can make sort of broad sweeping statements about that by looking at the interstellar extinction curve, which is here on the left. And the interstellar extinction curve is mainly a slope that extends all the way from the infrared here into the UV and the far UV. And the slope of it depends on the exact composition of the dust, the ratio between carbon and oxygen-rich dust, for instance. And but also grain size and other things play a role there. You cannot really say too much about the composition, the ratio between carbon rich or oxygen rich, until you start looking at spectral features in this interstellar extinction curve. So you have this feature here in the UV bond, which is thought to be due to aromatic carbon. And then here in this tiny little inset, you can blow up the interstellar extinction curve and see these two features here, a 10 and a 20 micron, which are due to silicates. So by looking at the relative strength of those features, people have already long worked out that the interstellar dust reservoir in our own Milky Way is about 80%, 2/3 to 80% made of amorphous silicates, and that the rest is predominantly amorphous carbon. There are some other components that might be there, oxides, there might be crystalline silicates. In fact, we'll talk about that later. There might be silicon carbide as well, which is related to the amorphous carbon. And then, of course, in denser regions, you may have, this doesn't really show very well, you may have additional features that you can identify in the infrared spectra. So here we have, you cannot see it, but we have 8 micron, 10 micron, 12 micron. This is the broad silicate feature, but you see substructure here and here and here and there and there. And those are ice features. So we also have, in some dense environments, we have ices present as well. Now, why are we interested in figuring out the composition? There's a number of reasons, but one important reason that I will emphasize here is that it actually provides you with a diagnostic tool. So, for instance, if we look at the crystalline fraction of silicates, we can say something about the formation history. And in fact, we can do that with any kind of composition. Any composition you find tells you about the formation and processing history of the grain. But specifically, when you look at crystallinity, you can say something about the thermal history that the grain has seen. So what do we mean by crystalline and amorphous materials? So silicates. So here we have the basic building block of silicate, which is a silicate tetraeder. So you have silicon in the center and 4 oxygens there at the corner. It's a cation, so you have to mix it with metals as well. And then you can make a lattice structure. So if it's a nicely organized lattice structure like this, so here we only show the silicate tetraeders, you get something like this, but you can also have some level of disorganization, and then we get something that still has the silicate tetraeders in them, but does not show much regularity in the lattice. If this is the case, then we only see resonances that are due to the silicate tetraeders themselves. So we see a 10 micron feature, which is due to the SIO stretching, and we have a 20 micron feature, which is due to the OSIO bending mode. If we have lattice regularity, then we see that those features are sort of splitting up into substructure, which is due to alignment in the lattice of these modes. Plus, we are seeing features beyond 30 micron, which are phonon modes, which are modes due to the lattice itself and no longer arising from the silicate tetraeder. So how do you form crystalline silicates? Well, for crystalline silicates to form, you have to heat them up to a temperature above the glass temperature, which lies around 1000 Kelvin. And then once you do that, the crystallization is pretty much instantaneous, at least on astronomical timescales, and you form crystalline material. So you have to be careful though, because if you heat it up to more than 1500 Kelvin, it actually evaporates. So it's a relatively narrow range. And so basically then you can say, okay, well, if you have, if the silicates form at temperatures above the glass temperature or are heated to these temperatures shortly thereafter, then the atoms in the mineral are mobile and you can form crystalline material. If the dust forms at very low temperatures, you have an immediate freeze out and you form an amorphous silicate. Now, amorphous silicates can also form later on. If you have a crystalline material and you expose it to cosmic ray hits, it could become amorphous later on, provided you keep it at low temperatures. So prior to JWST, what do we already know about the composition of interstellar, the composition and other properties of interstellar dust? And I only focus on points that are relevant for this work that we are talking about today. Well, if we think about the silicates, what we know about the interstellar silicates is that it's mostly amorphous silicates, and we can put a constraint on the crystalline fraction that it is less than 2%. So here are some examples of, I keep pointing with this finger, but it's not working, of the silicate feature. Well, it's actually the same feature. This is the feature observed towards the 10 microfeatures observed towards Sagittarius A star. And it's been fitted with different grain shapes of amorphous silicates. So spherical grains, Gaussian random field particles of 2 different kinds, and a distribution of hollow spheres. And in all cases, we find a very good match with the non-spherical grains. So these 3 panels even being much better than the spherical grains in fitting this feature. And this demonstrates that there's really no room for crystalline silicates here in the spectrum. I will show more of this later. So good fit is achieved with just amorphous silicates. However, we do know that in external galaxies, this is a different matter. And about 1/3, 1/4 to 1/5 of the galaxies observed with Spitzer show crystalline silicates. So this is work done by Henrik Spohn, who first detected that in 2006 and then put out a catalog a couple of years ago, going through the entire Spitzer archive and analyzing more than 3,000 spectra. And in 1/4 of these galaxies, he found evidence for crystallinity. And what you can see is basically, again, you have the same 10 micron feature here, 20 micron feature there, but you see substructure here now, there. And he was able to align it with, so the red curve here is the residual signal from the external galaxy. The purple line is the spectrum of a crystalline silicate. So it lines up perfectly. And indeed, a large number of galaxies do show crystalline silicates. Of course, Spitzer did pointed observations. So people selected these galaxies. There's some selection bias. So we don't know whether this is 1/4 of all galaxies or just 1/4 of the already somewhat special galaxies that were targeted by Spitzer. But still, a substantial fraction and at odds with what we see in the Milky Way. So then we want to look at the interstellar silicates in more detail now that we have JWST available to us, and we want to dig deeper into these questions. So we have studied the interstellar medium. Now we want to focus on the diffuse interstellar medium, so lower AV sightlines. And we want to know if the dust properties in these lower AV sightlines are the same as the denser sightlines that have been studied so far. And then is the crystalline fraction of the silicates in these sightlines the same? Is it possible to detect any nanosilicates in these sightlines or any environment at all? They have not been seen yet, but they would be sort of the smoking gun of grain formation. And then coupling back to the big questions, what does this tell us about the life cycle of dust in galaxies? So we can use JWST MIRI for this. It has the medium resolution spectroscopy mode for this, which allows us to do spectroscopy from 5 to 28 micron with a resolution of a couple of thousand. So if you have, so nice picture of JWST here, and if you have the focal plane here, the MIRI instrument sits there. In the observing proposal that we put forward, we also did observations with NIRCam, which sits there. The resolving power of a couple of thousand is well suited to study the mineralogy of interstellar dust, which needs in excess of about 500. So we're easily achieving that, especially if you're interested in the crystallinity. So the observation strategy that we do is we actually look at background stars and use the foreground method, foreground shield method, to actually study the interstellar dust composition. And in addition to the JWST MIRI MRS spectroscopy that I just mentioned, we also did near-cam spectroscopy to do the near-infrared part of the spectrum. We have HSD STIS spectroscopy as well for almost all the stars in our sample. We have VLT X-shooter observations, spectroscopy over the full UVB visible near-infrared wavelength range for the southern part of our sample, and a similar data set from the Himalaya Chandra telescope for the northern part of our sample. And the spectral resolution for all these observations is a couple of thousand. So this all matches quite nicely. And the target selection for the WST program, that's what we called it. So WST stands for the Web Investigation of Silicates and Carbon in the Interstellar Medium. And I guess the collaboration is rather alcoholic. So it's that's where the name comes from. We wanted to select nearby OMB stars, so within a few kiloparsec. We did this by combining Gaia data with 2MASS data to select, based on colors, objects that we think do not show winds or stellar photosphere features. They have no strong infrared access. They were just naked photospheres. That's what we were hoping for. And then we also looked for the diffuse ISM. So we didn't want molecular clouds in our sightlines. And we ended up, so this is the color selection that we did, but you see you still have more than 12 stars. So applying the other conditions, we found that we were left with this sample here that are divided over the sky like this. And here are they in the galactic plane. So 12 OMB stars. They are not well-known OMB stars because the bright OMB background stars that have been used previously with Spitzer, with ISO to study silicates and other features in absorption towards background stars are simply too bright to study with JWST. So we had to create a new sample which provided us with additional challenges because these background stars were not necessarily well characterized. So we were hoping we were selecting more or less naked stars. But I must say, we do have someone on our team, or a couple of people on our team, who are focusing on modeling the stars in more detail in the infrared, which is a challenge in itself. Okay, so then we put out a first paper last year describing the sample selection, describing the program, describing the intentions of the program. And this is what the spectral energy distributions look like. So here we have two objects in our sample. So you can see all these different parts. So the HST, JWST observations, and not everything is included here in these plots, but you get an idea. If you compare this to the actual spectrum that we think we have for the background object, you can see that there's a lot of extinction in the UV here, the optical, and then towards the infrared, the extinction is diminished. So you see a nice representation of the interstellar extinction curve there. In this paper, we started analyzing the first spectral features, and we started with aromatic hydrocarbons, which we have fitted here. So these are features around 3.4 micron. That's indicated by this arrow. In the SED representation here, you don't really see anything, but there's really a feature there, albeit weak. For this work, we're looking at the silicate feature, and you can just about make it out. So it's just this slight indentation here at 10 micron. Of course, there's also a 20 micron feature, but the JWST spectrum is actually getting so noisy at 20 micron that we cannot do this. So we're focusing on the 10 micron feature only. Yeah. All right. So what are we doing? The analysis of the silicate features is pretty simple in principle. So we are fitting a continuum, and then we are calculating the residual optical depth, and that we are fitting with a linear combination of opacities due to a variety of materials, silicates, crystalline silicates, nanosilicates, silicon carbide. So we're throwing in all these things, and all of them are pretty straightforward to put in. We take lab data, we assume some grain shape, and calculate that. For the nanosilicates, we have to do something special, so I'll spend some time on that. But this method has been applied before, so I've done this way back when in the ISO days to determine the crystalline fraction towards Sagittarius A star. It's exactly the same method. So in order to characterize the nanosilicates, because they haven't been measured in a way that we can use them, so there are no laboratory spectra available, we have to do calculations. And here is where the collaboration with Stefan Bromley's group at the University of Barcelona comes in. So they have been calculating the infrared spectra of nanoparticles, of silicate nanoparticles. So first, they calculate the structure of small particles, and they made a whole library of small particles, different compositions and different structures. So for each composition, they would calculate like the 5 lowest energy structures or something like that. And then they did, with a harmonic approximation, calculated the infrared spectra for these. And for each and every nanosilicate, the spectrum looks different. So unlike the pHs, where you start seeing families of features, you don't really see that in nanosilicate spectrum. Also, they extended this to larger clusters, but they had to apply a different method to do this. The structures were calculated in a different way. They were just growing them bit by bit, colliding silicate groups to monomers to the already existing structures, and then calculating the new structure that formed the actual structure of this using chemical modeling. And then once you have that structure, you can compute the infrared spectra again. From what I understand, the infrared spectroscopy calculations are more CPU intensive than the structure calculations. So they prefer to first settle on what structures might be there and then calculate the infrared spectra for what they think might be there. Then in his thesis, Joan Magnoso then actually made some plots where he looked at some average compositions or stacked together spectroscopy at different sizes. So he has here, for instance, for the pyroxene silicate composition, he has grains of sizes of 0.5 nanometers, 0.7, 0.9, etc. nanometers grouped together and calculate an average spectrum for these. The same for olivine. And then you see here that you have 2 features initially for the smallest grains, and then as they grow larger, these 2 features start to merge. You see the same behavior in the olivine grains. So he fitted that with some simple model to calculate where the peaks are, what the width are of these features, etc. So to each of these profiles in the 10 micron feature, we fitted 2 Gaussians to this structure, even though they're not always clearly Gaussian. So then at distinct values, we have sort of the representation of the spectrum expressed in 2 Gaussians. And then using this, I kind of interpolated the parameters of these two Gaussians to be able to estimate the intermediate values. So we have the amplitude, the wavelength, and the width of the first Gaussian, and the amplitude, wavelength, and the width of the second Gaussian. And here we have the grain size, and here the parameter that we're interested in. So I made all these fits and was able to express this as some sort of formula. So for any given grain size, you can calculate now what the spectrum looks like. Right? So what I did was I used to represent the nanosilicates, I used the grain size and a scaling factor. So two parameters rather than just one in the model. And doing this, we were able to create a fit. We used the nested sampling technique to create the best fit. And then we removed components and evaluated the difference in fit quality using Bayesian invariance to assess the quality of the fit with and without this particular component to figure out whether that component was really needed. The nanosilicates in this, so this is the best fit with all the components in for a particular sightline. The nanosilicates here are this brown feature that seems to consist of two components. Those are the two Gaussians. So we clearly needed it. Well, I'm going to show you that we clearly needed it, but this is the best fit that came out. Then we did this evaluation of fit quality. And this is what we find. So the evaluation color coding is here. So red really means strong evidence that this component is not needed. And the more you go to the green is strong evidence that this component is needed to make a good fit. So what we're finding is that for all the sightlines that we looked at, we have strong evidence that nanosilicates are needed. So we were very happy with that. We also have in some sightlines evidence that we need some small amount of phosphorite, and that gives rise here to the crystallinity column that we have. I also included diopside, but I think I should remove that because diopside requires calcium, and I did not put in any abundance constraints on the calcium, and of course calcium is much less abundant than silicon or magnesium or iron or whatever. So this is probably not a good representation for that. We also tried silicon carbide. We have some sightlines where there's a small amount of silicon carbide. Okay, so what amounts are we talking about? So the previous table showed evidence that it was there. This table shows the amount of nanosilicates that we find. And we find of the order of 10%, basically, in the sightlines that we're interested in. Note that I also included Sagittarius A star here, because I fitted it also, and we find a much lower fraction of nanosilicates. Sagittarius A star does show some phosphorite to be there of the order of 1%, which is within the limit that we said 20 years ago, which was less than 2%. The other sightlines do not really show evidence for phosphorite except here and here, which maybe contain a small amount. Right. So, okay, so that's the main result. The other result is that we were able to constrain the nanosilicate size because remember that was a free parameter, and we find that it's around 0.7 nanoliters. Right. So we looked at the nanosilicate fraction, the weight percentage in nanosilicates as a function of extinction. We do not find any correlation in that. So this is a plot that also going to go in the paper, but we do not find that there is a strong trend with that. Although again, the Sagittarius A star sightline, which has an AV of more than 30, actually has very low nanosilicate content. So eventually down here, the line goes down. This may be because Sagittarius A star actually contains molecular clouds, whereas here we are looking at diffuse, purely diffuse sightlines, or so we think. So maybe there's some explanation there. So that's basically summarizing what I just said. So in the diffuse ISM, we find 10% nanosilicates and less than 1% crystalline silicates. If we look at the Sagittarius A star sightline, which we fitted back in 2004, we fitted it again now, including the nanosilicates. We find that we need, depending on the fit that we do, between 1 and 4% of nanosilicates. So here is Sagittarius A star. And the crystalline fraction is less than 2%. In fact, the value that I just showed you in the table was basically 1%. And this sideline contains molecular clouds. Okay, so now why is it interesting to actually detect nanosilicates? Well, the problem is that if you look on a galactic scale at the interstellar dust reservoir, which has a certain value. So, for instance, if you look at in the high redshift universe, we find that there are some galaxies that have 10 to the 8 or 10 to the 9 solar masses of dust in them. This has been detected in submillimeter interthermal emission from the dust. If you look at the cumulative dust production coming off supernovae, coming off stellar winds, and you add all of that up, you are not reaching that interstellar dust reservoir, at least not in the time scale at which these of 1 gigayear, which corresponds to a redshift of about 6, which is at which these galaxies with 10 to the 8, 10 to the 9 solar masses were found. So there's a gap here between the dust production from stars, which are thought to be the main sources of dust, and the dust that we find in the interstellar medium. Also, locally in the Magellanic Clouds and in many other environments that people have looked at in the solar neighborhood, etc., we are not able to reconcile the dust production by evolved stars and supernovae with the interstellar dust mass. For example, one of the outputs of the SAGE survey of the Magellanic Clouds is that the interstellar dust mass is of the order of 7 times 10 to the 5 solar masses. The dust production is a few times 10 to the minus 5 solar masses per year. And the star formation rate is a few times 10 to the minus 4 solar masses per year. So from these numbers, you can calculate what the replenishment timescale is. So the replenishment timescale is a few times 10 to the 10 years. So this is the amount of time that you need to replace all the dust in the interstellar medium with freshly produced stellar dust. And that is actually, the age of the universe or more, right? So maybe if you're, the age of the LMC is 10 to the 10 years. If you are generous, you could say, okay, maybe it's just about doable, no? But of course, this does not take into account dust destruction in the interstellar medium. So, which is believed to be a factor. Also, the astration timescale, which is the timescale on which dust is being consumed by forming stars, is much shorter. So you're really having a problem in explaining the dust reservoir in the interstellar medium. If we also look at it from a modeling perspective, we find more or less the same thing. Schneider et al. In this work, we looked at the dust production and dust yield from a population of stars that was kind of forming following the star formation history that was observationally derived in 2009 by Harris and Zaritsky. We used that star formation history to sort of model the evolution of a population of stars and then the production of dust from this population of stars. That was so the theoretical dust yields of AGB stars. And then you form this this band of possible outcomes, which just about matches again the interstellar dust mass that we measured in the LMC. But again, this is without taking into account that destruction of dust is a factor in the interstellar medium. So we have a problem here, and there's like a myriad other lines of evidence here that as soon as you start taking into account that, we know dust production is happening, we see regions that are shocked by supernovae supernovae shocks traveling through them, that, the dust is actually forming gas phase, silicon oxide, etc. So we know that dust is being destroyed, but because of the low densities, we are not sure that it actually reforms in the interstellar medium. So the idea is, here is another line of evidence. If you look at the composition of dust, for instance, in the Magellanic Cloud, that is being produced by AGB stars, you find that it's actually predominantly carbon-rich, whereas the composition of the interstellar medium dust is more oxygen-rich, which is pointing more towards a sort of a massive star origin of the elements. So that's another reason that the interstellar dust reservoir is probably not all due to stellar dust production. So the significance of finding nanosilicates then is, well, as I explained before, multiple lines of evidence are showing that dust formation has to occur in interstellar medium to explain the observed dust reservoirs. But we have trouble explaining this theoretically to come up with dust condensation models in these conditions, and also it's not been observationally proven either. So to detect nanosilicates, that really points to the transition between solid and gas phase, between the constituents that silicates are made of and the bulk material silicates. Nanosilicates fill that gap in between. So it's kind of a smoking gun for interstellar dust production or dust destruction, of course. It is in between. It actually points to this transition between these two components. But having a population of 10% of these grains is really significant, and we can now try to include that into the models that we have that explain dust processing. And like I said, it provides a connection also to dust processing timescales if you have to update your dust formation timescales and mechanisms. So like I said, nanosilicates have not been directly detected yet. So nanodust is commonly seen in the form of pHs. So pHs are structures that look something like this. The polycyclic aromatic hydrocarbons, they consist mainly of carbon. They have hydrogens attached on the ends. And because of their regular structure, you see that their resonances sort of group together in broad bands. And even if the individual pHs are different, sort of the resonances do line up at roughly the same wavelengths. So you get these broad features, which are easily recognizable in astronomical spectra. These are commonly seen, and they are a form of nanograins. They're just not nanosilicates. Nanosilicates, though, have been proposed as a carrier for the anomalous microwave emission. So that is the emission that is seen in CMB experiments, for example, where if you look sort of on a large scale, you have thermal dust emission here. On this side, you have free emission here. And rather than that things connect here, there seems to be some sort of excess which remains unexplained. And that actually lines up quite nicely with the emission that is arising from, for instance, pyroxene nanosilicates or olivine nanosilicates at 20 Kelvin. Unfortunately, we do not have spectroscopic information on what this AME looks like, so we cannot match it up with the spectra that have been calculated here or any other proposed carrier. So it remains at this level, a proposal. Then I also talked about the crystalline silicates. So there is a need to further constrain the crystalline fraction. So this is still a work in progress on the data that we have. The reason that this is important is because it helps us to constrain the immobilization timescale. If you can really pin down what the crystalline fraction is, how low it is, so we know it's below 1%, but how low is it below 1%? And we compare this to the production of crystalline silicates by evolved stars, we can figure out how long it takes to actually get to that low level if we know other factors as well. In fact, we need to do something like this. We have the interstellar dust reservoir of crystalline silicates and amorphous silicates, and then there are several things like the dust production by evolved stars. We have the transition from crystalline to amorphous and from amorphous to crystalline, and we have destruction of crystalline material, and we have interstellar dust formation. We have to solve an equation like this to figure out what the interstellar amorphization timescale is. This is an important diagnostic tool because in starburst galaxies, and we have done this calculation, you can actually calculate that because freshly ejected stellar material actually does contain crystalline material. So initially, the interstellar medium is somewhat crystalline, and over time it becomes more amorphous as the starburst dies down. So here we have dust production by the stars and the starburst. We have the silicate mass in the interstellar medium going up, the crystalline silicate mass going up, and then here we have the ratio of the crystalline and the amorphous silicates giving the crystallinity, and it can reach about 10%. And these calculations were done in response to the identification of crystalline silicates in the starburst galaxies observed in Spitzer. So once again, the results of this project so far is that in the diffuse ISM, so with extinctions of AVs between 4 and 8, we find very little crystalline silicates, less than 1% by weight, but we find about 10% by weight of nanosilicates, and the remainder of the silicates are probably amorphous. And then this provides us with the first direct spectroscopic detection of nanosilicates, which indicates that phase transitions in the diffuse ISM occur, phase transition between the solid and the gas. And we interpret this as smoking gun evidence for dust formation in the ISM, previously suspected to occur, but not yet proven. And meaning that stellar outflows are in fact not the only source of dust in galaxies. This project is still going on. We're going to improve the numbers on the crystalline silicate content. We're also going to improve our numbers on the nanosilicate content. Right now, I'm just allowing for one characteristic size of the nanosilicates. I want to extend this to allow for multiple sizes. So I'm still playing with that. And then this will help us to get a handle on, better handle on the immobilization and destruction and formation timescales in the interstellar medium. And this then has implications for galaxy evolution. On the one hand, the crystallinity. So to get good handles on things like destruction timescales, immobilization timescales, formation timescales, this will help us to accurately predict how much crystalline material may be present in a galaxy following a certain epoch of star formation. And this then helps us when we are interpreting the spectra of distant galaxies. And this is important in the context of PRIMA, which is still being considered by NASA as a mission. So here, the small plot here shows the crystalline silicate spectrum at 0 redshift. But if you take the two edges of where the features occur between about 8 and 18 micron, and you redshift it, so here is redshift, you see that it moves nicely into the range, which is here indicated in red, that will be observable with PRIMA. So we're going to have a machine that with PRIMA that is able to detect crystallinity very well between redshift 2 and 4 here, and also to an extent at even higher redshift. So this is going to be very nice, and then it will be a nice tool to understand star formation activity. And then on the other hand, if dust formation and phase transitions between the solid and the gas phase in the interstellar medium are quite common, which as they are probed by the nanosilicates, we have 10% of the silicates in the form of nanosilicates. Then that maybe means that the dust reservoirs are not as stable as we think they are. And given fluctuations in conditions, it's entirely possible that dust-free galaxies exist and are going to be quite normal, really. And indeed, JWST is starting to detect galaxies with very low dust content in the early universe. And this, of course, then has an effect on galaxy evolution. As I explained at the very beginning, the presence of dust regulates star formation. But these are all kind of sweeping, broad implications that this work may have. I think that's it. Yeah, conclusions and future work. So for this project directly, we are saying that, okay, we have the first direct detection of nanosilicates, which is present at about 10% level. Crystalline silicates are absent in the diffuse ISM. We can put constraints on that. And these numbers have implications for dust processing, dust destruction, and dust formation in the interstellar medium. Future work would include studying more the variation between sightlines, enlarge the sample size. Now that we have this machinery in place, we can apply it to all sorts of sightlines where we have a background screen and a background source and a foreground screen. And this will then allow us ultimately to update or improve our model of silicate processing in galaxies. And that's it. Thank you.
Thank you, Ciska.
Yeah.
Well, first of all, congrats for this amazing work. Well, you basically in this theoretical observational comparison, you choose olivine from one side and pyroxene from the other. It's important to mention what is the evidence we have in our own solar system and concerning the most pristine carbonaceous chondrites that we also know that get attached materials from the interstellar medium, even from comets, from Stardust mission that just brought comets from 81P Will 2. And basically, the evidence we have is that the primordial chemistry is made of olivines.
Olivines, yeah, okay.
But in particular, the evidence is that there is the magnesium-rich olivine.
Yes.
Particularly, I'm not surprised because between the pyroxenes, you choose enstatine. And there is not evidence at all of enstatine. Why? Have the answer. You are forming silicates in a very, well, in comparison with the region where the pyroxenes are formed, in a very oxidizing environment. So you end with fosterite.
Yes.
That is the magnesium-rich olivine. Even in carbonaceous chondrites or even in ordinary chondrites, we have the entire evidence that because of the temperature gradient in the protoplanetary disk from the outer fosterite-rich to the inner phyalite-rich, that is the iron-rich olivine, then you have all this processing, thermal processing, that is just, sublimating the fosterite over time when they are drift into the sun. And nearby the sun, you are enriching this olivine in iron, so producing phyalite.
Yeah.
And then we have two basic types of conduits in chondrites: the magnesium-rich olivine, fosterite, and there is another that are not so common, but it depends on the group. Could be in comparison just at 10%, besides 90% of austeritic, that is iron rich.
Yes.
And this is the iron because, this is consequence of thermal processing in the inner part of the disk.
Yeah.
And enstatite is not in on display.
No.
Because it's a mineral that is relatively minor
Yeah.
in contours.
Yeah.
And is more formed in highly reduced conditions.
Okay.
So particularly in bodies that have been like planetary embryos, the most reduced form in the inner disk region. So it's not surprising that this is a clear, perhaps, blank for your. So you are finding that exactly enstatite there is not at all.
No.
Because
yes,
we don't expect this enstatite.
No, but enstatite has been detected in some denser environments. So if you look at what we call planetary nebulae, which have nothing to do with planets, no, above stars, they do find some enstatite, but not as clearly as forsterite. We've also looked for firelight. So I did not include firelight in here because pretty much all evidence shows that any amount of iron, you can add a small amount of iron, and your infrared features start to shift. So you can clearly see when you have some iron in. We don't see that shift. So we are able to put strong constraints on it. The only place where they're now starting to detect firelight is in planet-forming disks, which aligns with what you were saying. But in sort of interstellar medium and in evolved stars, we don't see firelight at all, which is why I didn't include it. But I can totally run it with firelight in and see if we can detect it. Or we can put constraints on it.
Even the first absorption bands found in the literature come from the observation of Halley and all these comets that appear in the forsterite.
Yeah, it's all forsterite. Yeah, Hale-Bopp and yes.
And the second very brief question: what do you mean for nanosilicates? Do you mean tiny structures of, for example, forsterite?
It is basically something that is either forsterite or enstatite, so Mg2SaO4 or MgSaO3. No, so that's the chemical composition, but it doesn't have the stoichiometric composition, but it doesn't have the same regularity in the lattice because it's so small that the energetic most favorable.
Perhaps a better word could be amorphous nanosilicates.
Well, yeah, but talking with Stefan Bromley, he's very reluctant to call it either amorphous or silicate crystalline. No, so because it's neither. He says it just they're just nanosilicates. They have the same composition as silicates, but you should think of them more as clusters, as large molecules rather than small dust grains. They're not bulk material. They're so small. They have tens of, maybe hundreds of atoms in them. It's not really bulk material. So it's more like a molecule. Yeah, but with silicate composition. For instance, forsterite or enstatite composition. Yeah.
Please.
Very interesting. So I have several questions, but we start with the most pressing one, I would say. So you think that the detection of this nanosilicate is proof of the formation of dust, the diffuse ISM? This is what you are saying. So what are we talking about? Because to form dust, you need to have a condensation sequence. How do you do a condensation sequence with the diffuse ISM? What's your proposal?
So I'm thinking of this as the smoking gun evidence. So we see this stuff being there. So it tells us that there is a transition taking place between solid and gas phase. The condensation sequence is probably something like once if you have the nanosilicates and you collide it with additional dust forming molecules, they will stick because it is a energetically favorable reaction. I have not done the chemical calculations to tell you what the condensation sequence would be.
Because I thought that the main argument against this scenario was that it was really difficult to find the right condition in the diffuse ISM.
Exactly. So to make the first step is difficult, yeah?
Yeah.
So to go from, once you have a few atoms together, it's downhill energetically. So it's the first few steps go up energetically, and then it's downhill. But we see these fragments to be present there. So whether they are fragments that are the result of destruction, or that they are the result of fresh formation, we don't know. But we see these fragments to be there. So yes, I agree with you. I mean, it is difficult to form this. So the theory is not explaining this yet.
Okay, so
But it has to happen because we have these dust reservoirs that we have to explain in the interstellar medium.
I think I agree with you, but there is a problem with the dust mass as it's right now. I'm not sure that we miss the dust producers. I think we also have a problem in the way we compute the dust.
Yeah, that's a different story. That's another talk, I think.
Exactly.
Yeah.
So
Next week.
question.
Yeah.
Yes,
Yeah.
so just to finish with that, I
Yeah.
think that we know as
Yeah.
the diffuse ISM, you destruct the dust.
Yeah.
When you destruct the dust, the collision models of dust dispersion show that you create a lot of these very small
Yes.
fragments. I think it's whether they can give seeds to do more bigger dust later.
Yeah.
This is completely open, but the diffuse ISM for me is extremely difficult to imagine how you could condense them. Unless, as you said, it's not really dust, it's more like 100 atoms together, and then there are the seeds of further dust. So, like really dust, that we call it, like micrometer.
Yes. No, this is a challenge, obviously.
Yeah.
But I think it's very interesting, and it will help us to address some of these issues that we have. For instance, the difference in composition between stardust and interstellar dust, and the mismatch in masses, if you believe that. Yes.
I have a final point for the indicators.
Yeah.
I think it's also important. So you have several stars where you have been measuring this, and you have various content of nanosilicates, silicate. So could you find any clue of why some line of sites would be richer and others not? And could there be a correlation with the presence of dust producers on the line of sight or not at all? Is this something? Can you have an idea of what drives these differences? I mean, because I think we give an idea of whether they are formation or destruction.
Yes. No, so far the only thing I've done is, just a simple plot with AB, but I haven't looked. As you may remember from the one of the earlier slides, they were actually somewhat grouped together by chance. No, this. Oh, I should show this. I forgot about this slide. I think I want to highlight Joan Marinoso's work, a PhD student of Stefan Bromley's, who did a lot of the calculations of the nanosilicates. What was I going to show now?
Yeah, the stars, the description.
Oh, yes,
of the stars.
yes.
Yeah, there are 3 of them.
Yeah, so here you have a bunch of them here together, and these are also somewhat close, but here these are definitely along the same sideline. They're here. So I could try to see between these 3, do they have the same fraction or not? I haven't done that. So I haven't looked at, the relation with where they are on the sky. So far, I've only looked at the AB, which tells you about the ratio, the carbon over silicon content as well. So yes.
So,
Get on.
it's a very simple question. I was going to ask which is the origin of the nanosilicates. So for what you're saying, looks like more destruction of other grains than formation in the diffuse, right? But my question is very simple. So when you say 10% of the nanosilicates,
Yeah.
you mean of the total mass in silicates or of the total mass of the dust?
Which is the same, basically. Because we only looked at the silicate feature, yeah? So we isolated the silicate feature, so we are not sensitive to detecting carbon. So it's of all the components that contribute to the silicate feature, which are the silicates. There is a silicon carbide feature in there. We calculated that too, but it's minuscule. So it's basically of the mass of silicate. Yes.
Let's go. Wow. Okay. Last question, please.
Thanks for the help. I have just very last question. As far as I remember, the fraction of nanosilicates is different between interstellar and IEEC.
Yes.
I was wondering why are these.
So what I thought, well, the 1% is the value I got in the last fit that I did. So I think I also got, you know, some results that are closer to 4%. So, but definitely it's lower than what we find in the diffuse ISO, which is more consistently sort of 10%. So the idea is that the Sagittarius A star sightline, well, it goes through the galaxy all the way to the galactic center. It's a much longer sightline. It has 30 AD of extinction, and it also contains molecular clouds. So maybe there is something about that sightline, about that combination of having more molecular clouds, the mass fraction taken up by molecular clouds compared to diffuse ISM, that explains the difference. Although it's very hard to go down to 1% because it's not like it's 90% molecular cloud towards the Sagittarius A stars. Maybe half. Yeah. Yes. Yeah.
Okay, let's go for Ciska. Well, thank you so much again, Ciska. Ciska is waiting and wait for Ciska as well. You want to be the
Yeah, of course. So
you just need your stick.
I just need my stick, yeah.
Oh, there were some questions as well.
Oh, there was a question. Oh.
Lisa,
Are they still there or not?
probably.
Questions, great talk. So can you speculate? Oh, this is Lisa. Okay. Can you speculate on heat sources available to make them crystalline? Well, it's not clear that they're crystalline. Can you hear me, Lisa? I explained that before, no, to Joseph. Yeah. She's not there anymore. Okay. Can I read the other question? Because then I will just talk to her. Because she says here. Also, when you modeled enstatite, did you include clinoenstatite? Yes, I included both clino and orthoenstatite. I will go and talk to her. Yes.
Yeah. You should talk to many people here.
Yes. Oh, let me take this. Yeah.
Oh wait, no. Should I do this?
Yeah, you have to.